Hey everybody, this is Larry. This is me going over the weekly premium problem. I already solved it earlier, I kind of do this in reverse order because I do get a lot of comments and I try to be, accommodating. But in that, the video is very long. It took me about an hour to solve it. It's a very hard problem for me. It may not be hard for you, but, and for full, let me not have it block my face. But for full disclosure, you can watch or part of it. You could kind of see how I come up with each part and how long it takes, right? I think we just talked about it yesterday or the day before. We talked about how long it takes for Larry to solve a problem and when to give up and stuff like this. And yeah. And so, yeah, now you know that, I will grind it out. It also turns out that I solved this in O of 1 instead of there's some like simulation that's O of n log n or O of n or something like this. I don't know. Didn't really look at it because I did it the other way. But so the structure of this is going to be a little bit different in that I will explain my attempted solution, and then we'll go over the code and all this stuff. And then if you still feel like you just want to see Larry struggle, or just kind of see how each piece built on each other. And how I kind of came up with it at the end, then you could watch the live portion of it for sure. Cool. Let's get started then. And yeah, so basically the first thing I did, to be honest, and I said this during the live version as well, is that if I kind of did some like visualization here. Oh, maybe this thing is actually blocking the screen. I did some. Sorry, hang on. This thing is still blocking the screen. I did some ASCII art kind of explanation visualization because normally I would do it on paper, but I just want people at home to kind of see it, right? It's not a contest. I don't have to do it. But basically I just kind of play around with small examples. And the first observation is that given an n by n thing, r times c thing, let's say, and this is going to be a square, right? And then and then you maybe have let me change the colors up a little bit real quick, right? This actually took me a long time, to be honest, so don't feel so bad if you feel like like the benefit of me doing a video and other people doing videos as well is that they have infinite amount of time to understand and come up with these things, and then I could, if I was one of those people, I would try to sound really smart, like, yeah, look, obviously the next thing you do is this, and then and then you're done with 5 minutes. You're passively learning. But what I always say is, you should actively learn, because learning is not, learning to understand the solution isn't the same as doing it and learning how to do it, right? It's like I always use the gym analogy because it's a very, I don't know, most of the time it's a very good analogy. Is that like, just because you've read up on, you understand how an exercise makes your muscle do better, doesn't mean you're going to gain muscle. You still have to go out to the gym and do it and really kind of put in the work, right? Anyway, for this particular case, and it took me a while. You could watch the live portion. There's nothing hitting anything. The first observation that I would make is that assuming that max once is smaller than the square, in some parts of it, it doesn't matter what you do. What I mean by that is that, let's say it's 3 by 3, right? So you have 1, 2, 3 on the red, and then 4, 5, 6, 7, 8, 9, right? And then now, if you look at just one shifted over, unless you're doing something silly or unreasonable, then your next one is going to be 1, 4, 7. And if you look at only the blue ones, then it contains all the numbers from 1 to 9 once, right? Maybe maybe this is obvious, maybe this is easy, maybe this is an observation that people made very quickly. I did not, so it took me a while. So I think this is insightful a little bit. So then now, of course, if the length of the entire thing, changing colors, if this is C, no, this is R, sorry, whoops. Number of rows, and this is number of this is C, this is the number of columns, right? If R mod C is equal to 0, or if R divides C, what is the divide symbol again? Man. Oh, is it this, right? If this is equal to C, if R divides, oh no, whoops. I always C for this, but what is, let's say S for the side of here, right? If all divides into S, and C divides into S, then we're pretty much done, right? I think that's the divide into symbol. If not, then I spent an hour on this. I have not many brain juice left, so I apologize. But let's just say, you know, this is, if this mod S is equal to 0, then, right? You know, you get the idea. Don't want to, I mean, I don't want to get too pedantic. Well, I mean, it's not pedantic to wanting to get the symbols right, but without wasting more time in Google and stuff, right? So then we're done. But let's say we're not, right? Then that means that there is some leftovers. And what do the leftovers look like? The leftovers look like, I'm choosing a color, so hang on. So you know, you're gonna have something that looks like this, and basically the idea is that now you have some leftovers. This could be the leftover. Wait, let me rephrase this real quick. Everything inside here, it doesn't matter, right? Because everything inside here, it is even, right? Like it has a even multiple of S. You know, so then because that is just the remainder, and you divide out the remainder and so forth, right? So that's fundamentally the so then now we have to figure out, oops, how to fill out the stuff that's not the remainder, right? Because yeah, and just to kind of be, I feel like I wasn't super clear. So to be clear, what I mean here is that because inside we have all these rectangles and they'll fit. Okay, I drew them terribly, but let's say that this, you know, this fits perfectly, right? Pretend they're even, right? So then now this fits perfectly, and yeah, okay. Poor drawing aside, you get the idea. So that means that, of course, you can do the math on this, and we'll do the math on this later. But you can assume that it doesn't matter how you jiggle the pattern, you have the same number of ones in there, right? So then now that we get that out of the way, the hard problem is coming out the remainder, or what's on the extra stuff, right? So then now, so there are two cases, or there are a couple of cases, maybe not two. I think there are three, right? Well, not cases. Cases is the wrong word, but there are a couple of things to consider. Let's put it that way, right? There's this orange bit, right? This orange bit. Well, what is this orange bit? This orange bit is the overlap of the extra stuff here and here. So that means that any ones that belong in there gets doubled up, gets counted twice. What I mean by that is that, maybe I'll phrase it another way, right? So let's say, you know, we're trying to figure out the pattern right now. We're trying to figure out a pattern on an S by S triangle, or sorry, square that optimizes for the not the overlaps, but the leftovers. Sorry, the leftovers. But in the leftovers, there is this overlap in that, you know, for example, another way to think about or visualize it first is that, let's say, you know, this is the square, right? And you know, and I'm going to label them 1, 2, 3, 4, 5, 6, 7, 8, 9, right? And let's say if you have ones, I'm just going to write an X for the ones, right? You know, your goal here is to optimize this such that, oops. Yeah. This is a terrible drawing, but you know, or proportions. But you know, let's say these are the leftovers, right? And then now, basically, the pattern matters because, for example, if you have a pattern that looks like this, and during the live portion I go over this a lot, then that means that you get to use something like this part, right? Let me change the colors real quick. And of course, only this part is actually used. And in the same way, you use this part and the entire thing is used, right? And then here you can think about, and I skipped a box, which is here. Of course, then now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you have this pattern. Then you know here, right? But so the idea here, there are a couple of things. One is that you can see that some cells appear more than once, right? Even in the overlaps, and basically, ooh, whoops. Basically here, and you do the calculation, but you can see that cell 1 and 4, they will appear in the overlap. So that means that they appear a lot of times. And what I mean by that is that it's going to appear, so this one, it's going to appear in all over S kind of times or something like this. Of course, you have to, you know, and we'll go over that in fully, but 1 and 4 will appear the most, right? And then the second question is, after that, what numbers appear the most? And that's basically the idea behind the rest of the problem, is that, well, if you have a longer side, let's say C is longer than, let's say C, what happened here? Let's say C is greater than R. If C is greater than R, then if you kind of, you know, let's say we, let's say we figure out the pattern differently, right? Instead, now we kind of, you know, greedily choose what we want. So greedily choose what we want. We start out with these 1 and 4 because, well, 1 and 4 appears the most, right? And then now, what appears the most next? Is it 2 or 3 or 5 or 6 or is it 7 or 8 or 9, right? And here, that's basically you know, the case analysis part. Basically, if C is greater than R, then basically that means that there are more 2's, because if C is greater than R, that means that there are just more spaces to fill in. So then now you want the 2's, and then the next number is 3. And you know that this increases the number of 1's by either C or C minus, well, C over S minus 1 time or something like this, give or take. You could do the math at home, right? But the idea is that because there are more C's, there are more full boxes, just by definition, because there are more columns than rows. So then now you want to add to here. So then now you prioritize the 2 and the 3 and the 5 and then the 6. If all these are done, then the entire row, the entire bottom thing is filled. Then now we can prioritize, say, 7, and that's pretty much it. That's pretty much the idea. It's really, and obviously there's another case for R is greater than C, and you know, you just do it the other way around, because now you want 7 first, and then that's it really, because it only has 1 space. That's basically the core idea behind this problem, and yeah. And then now we'll go over the code, and during the live portion I kind of went over, and that's basically what this tries to explain. Hopefully this part is a little bit better. But yeah, and the idea, but all this after that is just math. So here, the first thing I did is that I actually, instead of kind of having an if statement about R and C, I made sure that C is greater than R. That's it. No questions, right? Here, basically, this is the number of full things with no, you know, you can think about this as like a diff mod thing. This is the number of full boxes that we have on rows, full boxes on the columns. And then the max 1, these are just, let me actually pull the drawing back real quick. Let me see if I can minimize this a little bit. Hang on. How do I move this? I cannot select it to move. Oh, excuse me. Sorry, friends. I cannot select it for some reason. Alright, there we go a little bit. I'll have to remember to move it back. But yeah, but basically total, this part is just everything that is this portion, right? The part that isn't the leftovers. Let me redraw that. Basically, all the stuff that is in the leftovers is this part. The math you can do pretty quickly and easily, and this is what I do, right? Because we assume that for each box, each complete box, we have the number of max ones. Here I count the double overlap, and that's basically just this box here in the part that has overlapping both the sides. I call it double overlap. I don't know, right? So if the two cases, and you probably don't even need to split them out, but I just wanted to kind of in my head make it similar. But yeah, you don't need to split them out actually, but I think it's similar to go. But basically, if we have fewer ones than this box, you know, in the 1-4, if you only have one number to fill and you have two boxes, then we're done, right? And this is it, basically the number of max ones, and then we just kind of count the number of rows and columns, because by definition this is smaller than the available space anyway. Otherwise, you know, here we do the math on the double overlapping part, and then now we have, you know, the number of ones that we have left. And here we go with the bottom space first, because remember C is greater than R, so we just do some math to kind of count the number of bottom space, the spaces on the bottom. In this case is basically the 1 to the 6. I'm drawing on the side. I don't know if you could see it. It's a little bit cut off, but you get the idea, right? Basically, it's just like the box that's here or whatever. Yeah, it's still cut off. Okay, fine. And then of course, how many we actually put on the bottom is just going to be the minimum of the number of spaces or the number of leftovers, whichever is fewer. And then we just do the math. This is the number of full columns, and then we put it to the bottom. We subtract that from the leftovers because we used them, and then we do the same for the right side. Yeah, that's all I have for this one. This is all of one or one time or one space, and yeah. What else is there to say? I think, come to think of it, the way that after I just talked about it now, I guess so one thing is that the constraints are only width and height is only 100. Of course, if you have all one time or one space, well, it doesn't matter what the width and height is. But I think what happens is that for you can actually in a greedy kind of way, and this is a very greedy problem, you can just count the number of times a cell appears, and then just greedily put it in. Like in the example that we have, you know, you can just kind of go like 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then basically draw boxes and even counting the overlaps and stuff like this. And because it's at most 100 times 100, you're going to have at most 10,000 entries. So then you're just sorting the 10,000. So it's going to be R times C times log R times C, and that will probably be the solution for like the sillier one that is an O of 1. But so this isn't necessary per se, but that's what I end up with. Yeah, let me know what you think. Let me know how you did it, and let me know if you enjoyed this video. It's very long, but you can watch me solve it live during the live solve portion now. Hey everybody, this is Larry. This is me doing the last premium weekly problem for August. I forgot the month. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem. You know, it's a problem that we haven't seen before, or I haven't seen before. So if you have seen it, let me know. But yeah, let's get to it. And it's a hard one, so hopefully it won't take me too long, because I kind of started on this one a little bit late. All right, 1183, maximum number of ones. Okay, so you have an M matrix, or matrix M with dimensions width times height, such that every cell has a value 0, 1, and any square submatrix of M of size of some side length times side length has at most max 1 ones. Return the maximum number of ones that the matrix can have. What does that mean? Let's see. I think I have trouble understanding this, but look at the constraints real quickly. That it's small enough that, I don't know, well, 100 to the fourth, it's gonna be too slow, so no brute force. But beyond that, let's see. Okay, so 3 by 3, any square submatrix M of size side length times side length has at most ones. To be honest, my initial intuition is greedy, but I don't know that that's true. Because this is definitely a problem that I think normally I would go on my paper and notebook to kind of draw it out, like a lot of scenario, and see if I could kind of disprove greedy, or at least find a counterexample, like that's which is disproving it. But I'm gonna do it, you know, on board to kind of, yeah, because I think it well, I mean, so that other people can see. Sorry, I'm like stuck trying to think about this one. So I don't know how to resolve this one off my head, other than maybe some idea of greedy. Let's say you have, I don't know, some big number and you have 2's, right? And let's say you have 2 by 2, that's 2. Then technically the first row would be all filled then. And then you have all 0's. And then that would actually be pretty optimal. So I think in this case that would work, no matter what the height or width or whatever it is. I'm trying to think, right? So let's say it is more sparse. Let's say we have 3 by 3, or we have effectively, the way that I think about these patterns is going to be infinity. But let's say we have a 3 by 3 and we limit it by 1, so it's always going to look like this, right? Like, it doesn't matter which of the 9, and in fact this has to, or not has to, but it is more optimal here, because if this is here, then it can only lead to a worse solution, because obviously you just move it here and then the next one is here, right? And so in that sense, greedy makes sense. But I think there is like weird cases. Let's say n is 4, or you have 4 cells in a 3 by 3. Then I would start throwing them out like this, right? And maybe right? So this looks good so far in the first 3 rows. Oops. But where we get in trouble maybe is something like this. Is that, because this is 4, this is 4, this is 4. Maybe that's still fine. I was thinking maybe there's some optimal way to kind of, well, we know that these has to be zeros just from here, so I guess maybe the greedy is fine. Because you always want to optimize for one of the, toward the edge, because if you kind of analyze it by 1 dimension first, right? You want it toward the beginning of the 1D array, because then now in theory it always leaves you with more room to go in the future. And then if you kind of extrapolate that to 2D, that said, that argument doesn't always work with respect to like, oh, if it works with 1D, then it works with 2D kind of thing. And that will always be the pattern, I guess. And then the question is, okay, so this is if it's perfect, right? So like, what happens if it's something like this? What if it's not, instead of not having 3 by 3, but on in a board of 9, we have a board of 8, right? Then now, the last cell is actually a little bit, the last row is a little bit sketch, isn't it? Do we do this? Is that right? No, because this cannot happen, because these 3 by 3 would have 5 cells. So what if I have a 1 here? Does that work? No, because these 3 by 3 would also have 5 cells, so it has to still be 0. So there's no way to get, so these all have to be 0 because of the constraint proposed by these in either case. I mean, you could obviously move one here, but that does not change. Does that change the outcome? No, because this still is 3, so it doesn't matter. Okay. To be honest, I don't have a great proof here, or like a watertight proof per se, but I think I'm okay with being convinced, because there's really no way, but because basically the last 3 by 3 I mean, I think I'm kind of convinced, but okay. And then the question is, how would you solve it, right? Well, then now you don't even have to, I mean, you could construct it with some sort of like dynamic programming lookup thing, or even with like seg tree or something like that. But I think now, then yeah, and you cannot rotate this. So if you have like and then you have just one more, it has to go this way. I mean, the alternative is this is a 0, but then that's clearly worse. So okay, yeah. So then it just becomes this tiling, right? So then you just do the math on the tiling, because this will always be like you get. The only tricky thing is about maximizing it when the input of width and height is not a square, because then it depends on the orientation of how you fit these things in. I think, I mean, I kind of chose greedy as the pattern here, but I think any pattern with m inside of m inside of this, oh wait, no, m. So any max ones inside a square of m is going to work. So it'll give you a solution, right? Any pattern that is smaller than that will give you a solution, because just by, you can kind of prove that because of like, you could kind of just think about almost like a sliding window, because we did sliding window at a problem of you have a m by m matrix, and then you shift one, but then you kind of think about it as shifting one as maybe I'll write it like this, as you just have 1 2 3 4 5 6 7 8 9. If you kind of think about shifting it, it really just goes to 2 3 1 4 5 5 6 4 8 9 7. So it will always have the same m by m cells, and therefore with that math, it will always have exactly max number of ones. Yeah, so it will always fit the constraint. It might not be maximal. The maximal comes from the fact that yeah, so you have to kind of figure out how to do the leftovers, and there are 2 ways to do the leftovers, right? So let's say you have something like this, and yeah, and maybe something like one more row, right? And then the other way could do it is just rotate it vertically. So you have something like this, and then in this case it would look something like this. And then you just do the math on both. I think in this particular case, they are the same, because of, you just move. Wait, is it? Yeah, because you just move this one to this one, and oh wait, maybe not. Huh. Well, it's either that or I misdrew it, to be honest. But yeah, but either way, that's why. So, but those are the 2 possibilities, I think. And so then we can test it after that. So let's try that. I mean, to be honest, right now, even though maybe I sound confident, I'm not confident at all. So, but especially for a contest, you know, I know I'm not in a contest right now, but for a contest, that's what I would kind of, that's what I would try to do. Okay. Yeah. So now we have this, right? So for R is equal to with height or in. Something like this, right? And the reason why we choose this pattern versus like a random pattern is, as we said, we want to shift everything to the left and we want to shift everything up. Is that even good enough? Maybe I'm wrong here though. Let me think about this. Let's say we have 5 elements, right? And 3. 5, like we have 5, so and a 3 by 3, right? So it looks something like this. It's not convincing that this is more optimal than, say, you know. Actually, I kind of did this wrong. Right? I mean, if they divide evenly, this is fine. If they don't, then what happens? Let's say we have 3 mod 1, or we have 1 remainder of 3. Then you definitely want 1 1 1s here. And not as opposed to, say, like 1 0 and whatever, right? Let's say we have mod 2, then does that matter as much? No, then you want 5 to be like this instead of like this. Because then now you can do something like this, right? Versus if you have this, then it doesn't quite work. Is there a case where this would be more advantageous? I guess not, because I think the idea is that you fill out, you minimize the number of rows, you know, or the inversion of it. You want to minimize the number of rows because then now your remainder will get as juicy as possible, I guess, right? But is that even true? Because you have, well, I mean, it is true if you're thinking about 1 dimension, but if you have 2 dimensions, then now, so then now the problem becomes, okay, let's say you have R mod side length and C mod side length, right? So then now, and they could only fit, you know, so then these only goes up from 0, which we don't have to care about because that means that it is optimal, or like any possibility is good. Or if, and we're just thinking about side length is equal for 3 for now. I'm just trying to visualize cases in my head as I'm solving this. So then now, so then let's say we have 1 left over. We have 1 left over, we all want everything to be 1, right? But, and we have 2 left over, we want, you know, everything to be on the first 2 rows for obvious reasons, and that's the possibility. But what if we have, but this is now 2 dimensions, right, as we say? So what if I have 1 by 1 left over? Well, if we have 1 by 1 left over, then it doesn't really matter, because then now our so on the last row and last column, we have, wait, is that true? Well, no, yeah, this is the case where you want it to look like this, because then now you maximize your last usage of the last row and last column, and this would be suboptimal because then now your last row would look like this, but then your last column would look like 110 or whatever, right? And then alternating or whatever. well, not alternating, but in that pattern. So it will look something like this. So then now the problem is actually how do we fill out these, right? So for 1 by 1, we actually want this particular case because then now the last row will be 1, 1, 1, right? Yeah. Wow, this is a hard problem. I thought maybe we could brute force it, and maybe we still can in a smarter way, but not in a naive way. Good thing to know is that n is equal to 100, so maybe there is something that doesn't have to be super efficient. Yeah, and then if it's 2 by 2, then or 2 by 1 first, right? Then the first thing doesn't matter. Right, but then the last 2 rows, or if we do 2 by 1, then we actually want something. Yeah, actually this is just this, but right, and so then here this is 4 or 5, and this is all 3, right? For height, and then now if it's 2 by 2, then now you get into this trouble of this is just 1. How does this look? This is 1 1 0 1 1 0. Is that true? Did I mess this up? Something feels a little bit off for 5. I think I messed this up. The last. This is also 1 1 0. I think. For 5, yeah. Well, maybe it doesn't have to be. If this is, but then now it becomes like, what if it's this? Oh, okay. I'll use 2 different things so that it's a little bit clearer because I'm just confusing things now. Right, something like this. So you have to choose between this or using this pattern again. If you use this pattern, what will yield you? It will yield you. It's basically the same except for but now this part is much smaller, right? And so for mod 2 is left over is 2 and 2. You actually want this thing again, I think. Yeah, I mean, I think this one is strictly less than because you can move all the ones from here to here as we did, but here we just on the rows we strictly subtract 1. I guess we can we simulate? How do we simulate? So we know the mods, right? If we know the mods, then we can just see if we can fill it up. So then we know that the longer side. Okay, so we know the longer side of, or the height of width, whichever is longer. In that case, we've filled that up. Well, in that case, we basically we can calculate this overlap in the corner and then fill that first, right? So that means that for here, we want to fill the things that double counts, right? So which is a 2 by 2. So we have 2 by 2 mod, then that means that 4 of them are the overlapping bits, and therefore we want this corner to be 4 by 4 because we know that by definition those are used by 2 things. So then that's here. And then after that, it doesn't really matter what the, well, I mean, it matters, but like it either goes from either here or here, and it matters, okay, it actually matters because it's clear, but then now we just fill up the rows instead. Okay, I think this makes sense. I don't know that I explained it very well. It's a very, at least for me, it's a very tough problem. So it's earning its hardness. Well, let's see. Right. Okay. So, and we're basically here. It's just enumerating for B side. So it doesn't really matter. Though maybe the way that I wrote it, it doesn't really matter. Maybe I don't need to do this depending on. We can actually just do this in a different way. In that width and height doesn't matter because everything else is a square. So basically we can do something like this is max of width height, and then I like it the other way around actually. So that this is a longer, so you have a longer matrix than whatever, right? So then now, what does this mean? That means that we have 2 by 2 cells. So yeah. So max ones, right? Okay, so now we're just counting the core part, which is the stuff that's inside, right? So and that part is easier because full R is equal to R divided by side length. Full C is equal to C. So this is just the number of full squares that are basically in the parts that doesn't matter because it always have max 1 once. So then now, so total is equal to times times max ones so far, right? But then now we have to count the extras. And here, we will fill this as much as possible, right? So this is the double counted piece. It's so easy to get wrong. That's why I'm trying to slow down a little bit and hopefully get it right in the first try and not, silly wrong mistakes. It's something that I'm bad at, so I'm trying to, yeah. How do I do this, actually? Well, I mean, basically, the double overlap, say, is equal to R mod side length times C mod side length, right? If max ones is greater than double overlap, or if this is less than double overlap or equal to, then we're basically done, because that means that we have no, or everything that or we put all the ones down in the places that double overlap, so then it also goes expands out as well, which means it's good. Then basically we have let's see, that means that we have another full R. So how many extra column squares are there? Well, it's just, yeah, full C times full R, or full R times full C, times max ones. And then because we have double lap, so this is this minus 1, maybe this minus 1. Right, and that should be good. Just add an extra parens. Right, else, which is the hard part, else, let's see, right? Else, it's not that, we already conceptualized and visualized it. It's just I'm really bad at math, so I have to really think about or I'm really slow at it. Okay, so basically the column ones, right? So the column ones will have, so there are full C number of them, and as we said, there'll be more C than R's. That's by design. So there's C of them. Technically C minus 1 for the double counting one, but we'll keep it C. Let's just do C minus 1. So these are the ones. But even before that, we want it's not quite enough, is it? Because so in this case, well, we have a 2 by 2, so it doesn't matter, and it's 5, doesn't really matter. But if this is, if we delete this row, for example, even though this is longer, it is not the decision maker. Right? What is the decision maker? Decision maker? The number of space available, right? So how many spaces are on here? And we assume that this is going to be all filled because, well, that's just the definition of here. So then basically the amount of available spaces here is what we're trying to optimize, because we can only, by the definition of, we cannot fill, by the definition of that we have overflow, so that means that the double overlap part is all ones. So then we have extra stuff, so it either goes here to the left or the right, right? And this is hard. So that means that the number of available space is going to be, basically now we're just trying to figure out how many what is the impact of adding 1 0 to the longer side, right? So then now we have so Z zeros is equal to the number of columns times, I mean this is just minus 1, times the mod of, it's like side length minus R mod C or something, side length times side length minus R mod C, or something like this maybe, because basic, oh no, column, no, yeah, column mod is going to be, it's something like this, but also mod side length, so that if it's, because you can have side length number of rows, so if this is 0, then you're done anyway. But in that case, I think the double, I don't think this is possible to be 0, just because then the double overlap would be 0. So then oh wait, no, then I guess it always, wait, what? Wait, did I mess this up? I think, no, I think I messed up the sign, that's all. Basically, this is saying that we have max ones anyway inside the overlap. Wait, what is this part saying? I'm kind of confused now. This is just wrong, isn't it? Huh. basically what I wanted to no, this is, oh, I see. Yeah, okay. Yeah, no, this part is right, because then now if we don't have enough for the overlap, then that means that everything doubles. Okay, yeah. Or if it's Leetcode, then everything still doubles because it's fine. Okay, yeah. So that means that here we have more max ones than overlap. So that means we have extra ones, but and the number of possible zeros. I mean, that's fine, but I'm trying to think. Like, I mean, it is greedy, for sure. But I'm trying to quantify the exact choice that we're trying to make here, which is that, okay, let's say we have, if we want to convert one of the zeros on the longer side, or one of the zeros on the height, right? And then we just basically iterate on that. No, okay, yeah. I think this is why I had it originally like this. By definition of, that's why I wanted to okay. Okay, I think I got it. So basically, now we're trying to figure out how many. Okay, yeah. Sorry, I have to think for a lot of stuff. But basically, every time we add, we have a max one left over, and we put it on the longer side. Well, that will add full C minus one, right? So basically, this is the impact of adding one to the C side, and this is impact of adding one to the column side. So I think this part is fine, and we know that this is bigger than this, so we always want to full it for the first one. And you want to keep doing that as long as you can until this is full. So when is this full? So this is full when so we have full column length but trimmed height. So that means that, and the column length is just going to be, well, wait, what? No. I mean, yeah. Wait, what? Give me a second. Well, the full the length is the same as side length. That's why I got a little confused. I'm confusing a lot of things. This is kind of a hard part. All right, so basically we have side length, and yeah, so basically we have, okay, I see. Side length times side length is the number of total spaces that we have to add, right? And or that we have space to add max ones. So all right, let's calculate this. So leftover is equal to max ones minus double overlap, right? And of course, total space is equal to side length times side length, because you can think about it as a side thing, and not all of them is attributed to the long side, but this is space. Man, watch I look at the solution afterwards, and there's like some easy like 5-liner, and I'm just like, oh, did not understand it at all. But I'm trying to work through it, so hopefully this is helpful. It's helpful if you even hear, so I don't know. But okay, so this is the total spaces. This is the ones left over. And so we have to figure out, you know, calculate for to fit is equal to total space minus, well, it's ones left over, but it's basically, okay, so total space is this minus double overlap, right? Yeah. And then now we take the min of the total spaces or ones left over. Because I guess in theory, you can have someone just write max ones is equal to like 1 billion. I don't know. I guess they actually limit this, so that's not a possible case. So I think that's fine then. So this is the total space left, and then well, I guess we don't have to do the total space left then, because we can assume that ones left over is enough given that constraint. Okay, so we have ones to fit, right? And we don't put it on the full C-1 first because that's the impact that we get. So, how many times can we fill it before it's full, right? So that's side length times R mod side length, right? So we can do, so that's the number of extra rows that we get factored in, right? So that is the square, or not square, rectangle that we have on the extra. So it would be like maybe this or something like this. Oops. So if you have something like this, it would be one of the 3x2s is what we're trying to do here. And yeah. And basically, okay, we'll try to fill, we have to subtract that from, so we have to subtract this. So this is bottom space, I'll go bottom space. So you go to this minus the double overlap, because there's a double overlap of ones. So these are the number of bottom spaces we have on the bottom. And then, so total we added to bottom space, or we want the min of the bottom space or ones left over times okay, so here maybe I'll write put to bottom. Let's go to this, and then now put to bottom times that's the number of full things. So put that, and then now we can do one left over. We subtract put to bottom, and then the rest we just put on the column because we know that by constraint it cannot go over. Nope. And that's it. Don't know if this is right. It is of course not right. But alright, we made some good fun time. So let's see what's up. So max ones is 1, and we return 1. So we got, so this part I think is right. The double overlap. What is the double overlap? Oh, the double overlap is 1, right? Yeah, I mean we don't need to do that, do we? Both mod 2, okay. So the double overlap is, so this is true. Did I mess this up? So for R, we have 1 for R times 1. Oh, it's 1 times 1, but this isn't right. This is plus. Yeah, this is plus for each. Okay, yeah. This is why I tell you that things. Alright, I mean, better. Is this right? No. Yeah, no, because it has overlap. This should be right. So what am I missing? So it's giving 2. So this is giving 1 plus 1. Oh, because this is full. I think I messed up the because this is full R. This is the extra one, so you have to factor in the. Wait, what? Okay, so we have 1 full R on the overlaps. No, this should be right? I mean, well, it's not. So we have 1 plus... Oh, no, there should be 2. We have to round... Oh, okay. We have to round up because we don't count the overlaps. Or this doesn't count the overlaps because... Yeah. So we don't have to do subtract 1. In fact, we add 1 because now we count the overlap extra. Okay, yeah, we got that one fine. That's tricky though. Okay, so here we have 2, but we expect 6. Okay, so we have max once is 2. What does our code tell us? I mean, this is still even, so this is good. I suspect we have a lot of wrong answers on this one. But yeah, so this is 1 by... So the max one is going to be 1 by 1 times 2. So this is 2. The double overlap is going to be 1 by 1. So the double overlap is 1. Wait. Yeah, 1 by... This is also wrong, isn't it? Oh, no, this is right. We have 1 full cell. Yeah. So this is 2. The overlap, the double overlap is going to be less than, so we have to do this part. Yeah. Alright, that's good. I mean, better get the wrong answer during examples than, you know, afterwards. But okay, so the ones left over we have, so max once is 2, the double overlap, which we would put on everything. Maybe I missed, I think I missed a step. Yeah, okay, I see why. Because I didn't actually count the double overlap part. So then now we have the double overlap, right? And you have to do this thing. Yeah. Okay, it's still wrong, but maybe it's a little bit closer. Okay, so the double overlap in this case is going to be 1 for the corner. Fair enough. You have full R, full C. So that gives us 1, 2, 3, 4, 5. So then now it has to find this. So then initially we put the bottom. So maybe this is where it gets a little clunky. So side length is 2 times. Where do I get times from? This form is just wrong. Oh, wait, no, I was thinking of something else. This is where I had before. Okay. So, the number of bottom spaces. So, this is one the side and this is the other side, right? So, R mod side length. The number of rows is, I mean, this is going to be 1. As always is 1. And then the side length is 2, so this is 2 by 1, which is true. So we have 2 spaces, the double overlap is 1, so bottom space, we only have 1 space left over. Put to bottom is going to be, so we have 1 and 1 overlap, 1 left over. It's going to be 1, right? So this is 1 times full C minus 1. Yeah. So this is 1 full C. No. I confused. I named them full C. They're full, so this should be good. I don't know why I keep on adding 1 because subtracting 1 because I double count the overlap. But all right, I think we're Gucci here. Let's give it a submit. Oh no, I mean I was gonna say my idea is what. My implementation finally matches the idea, but maybe we're off by a little bit. And only 61 out of 105 cases, so we did a lot, but not enough. Okay. Or rather, that means that our algorithm is just fundamentally a little bit incorrect, because that means that because if you're doing better than the answer, it means that you have an implementation error somewhere. The reason being that yeah, you can do better than optimal, unless your logic is just, or your coding is wrong. If you do suboptimal, it may mean that your strategy is wrong. But here it just means that it's probably the mathematical part that is wrong. I mean, it could still be both, but that is at least the first part, right? Okay. Yeah. Okay. So I guess we just have to print a bunch of stuff. So double overlap is 8. And one's left over. Bottom space maybe. Let's start with that and then we'll see. So bottom space is 12. Why is that? So it's 4 by 2. Wait, what? Why is it 12 if it's just 10? Isn't it 4 by 2? Where do I get 12? Okay, so which one is all again? Oh, it's the minimum one. So then now you have 52 by 74. So then you have 2. Oh, I see. So basically it's a 2 by 10, and then the double overlap is 8. So that means that you have okay. So you have 12 left over. Wow, that's a lot of ones left over. Oh, I guess that's fine, to be honest. Oh, I messed this up. That's why. Because we have to do I see. I assume that you cannot go over, but I'm wrong here, because it cannot go over side length square, but it can go over this. So okay, so I'm actually happy in a sense that like this is tractable, right? Like we can figure it out. Or this is the same idea as here, which is that okay, fine. Right space is equal to side length times c mod side length minus double overlap, right? So then now we move that first, and then put to right is equal to min right space, one's left over, and then now okay. I was just being lazy, to be honest. I thought that that made it constrained, but I just was wrong, and now it works, or at least for that test case. That was a silly optimization, that's all. Wow, I mean, that was a very hard problem. I end up spending 15 minutes here. Probably the longest I've done in a while for a problem that I ultimately solved anyway. Yeah, I mean, this is just case analysis, I think, and it becomes greedy. This is a very interesting problem. I don't know that there's a TLDR for me, other than kind of constructing everything step by step. I'm going to re-record the beginning of this video, so, or if you're watching this, you'll actually get this video with an intro. So if you're still here, let me know what's your favorite sports that you've been playing lately. It could be outdoor sports, baseball, softball, hockey, or skiing, snowboarding, whatever. Let me know in the comments. I've been doing a lot of softball and a lot of hiking. Yeah, and I'll give you some like mental props for next time or something. I don't know. But yeah, this is all of 1, right? So it actually didn't need things to be 100 by 100. Maybe there's a simulation one. Maybe that would make it easier, but everything I do is all of 1. So maybe there is a simulation one. Let's take a look real quick. Basically the same idea I have so far. Oh yeah, and then they... Okay, so they did it this way. That's why it was much easier, because they simulated it. Or like, yeah, okay. But yeah, I did it with O of 1, so I don't know. Yeah, this is probably the same as this person. So yeah, O of 1 time, O of 1 space. Let me know what you think. And yeah, stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.